Hello, everyone, and welcome to another Virtual Science on Tap. I'm Linda Deck, the director of the Bradbury Science Museum here at Los Alamos National Laboratory. Science on Tap is your opportunity to hear from the experts themselves the cool new research going on here at the lab. Today's topic, exploring our solar system through gamma ray and neutron detection by Suzanne Nowicki. Science on Tap is a program of the Bradbury Science Museum here in Los Alamos with support from the Los Alamos Creative District. Many thanks to Lauren McDaniel, the Los Alamos Main Street Director, and the Los Alamos Creative District Curator, Jeremy Smith. Here's Jeremy to tell us more about upcoming Creative District events. Jeremy?
Thanks, Linda. Thanks for hosting Science on Tap, as usual. Always a great presentation. So my name is Jeremy. I'm with the Los Alamos Creative District. And 2 weeks from now, February 22nd, we've got Nature on Tap with the Los Alamos Nature Center. And that is going to be a geological tour of northern Jemez Mountains. Local volcanologist and geologist Kurt Kempter will be speaking that evening. And then also, March 22nd, we've got History on Tap coming up, and that is in partnership with the Los Alamos Historical Society. If you'd like to keep up to date on all of the On Tap series, we've also got Culture on Tap, as well as the Science on Tap each month. And you can go to the creativelosalamos.com website. That's creativelosalamos.com. Sign up for our newsletter. I'll send out a reminder for each of the events that we have going on. You can also follow us on Facebook and get updates on the events that we're hosting. So once again, my name is Jeremy Smith with Los Alamos Creative District. I hope you enjoy another amazing Science on Tap. And back to you, Linda. Thanks.
Oh, Jeremy, thanks so very much. Those sound like great programs. The next Science on Tap will be the third Monday of March, which is March 15th. So on the Ides of March, Alex Jonko with the lab's Computational Earth Sciences group will present new information on the behavior of wildland fires using their award-winning model, FireTech. He'll help us understand the latest studies of how forest structure and fuel distribution affects fire behavior. So here's how Science on Tap works. You're here having a good time. That's the first requirement. Thank you for joining us again. Our presenter will give a 15-minute overview of her topic, and then it's up to you to ask questions and keep the conversation going, according to what you and your fellow attendees would like to learn. So write your questions into the Q&A, and I'll bring them up and feed them to our presenter, and we'll learn more by what is interesting you. So I hope we have a lively conversation. Our presenter today is Dr. Suzanne Nowicki, a nuclear physicist in the Space, Science, and Applications Group here at Los Alamos National Laboratory. Suzanne has long been fascinated by space. During her youth in France, she'd regularly engage in planet watching with her grandfather, who was a high school physics teacher. She'd look forward to him setting up his telescope and looking through it with him as often as possible. She said after much begging, she finally received her own telescope from him on her 16th birthday. Suzanne pursued her passion for planets and received a doctorate from the University of Michigan in applied physics. She has more than 13 years of experience in the space sciences with expertise in nuclear instrumentation design and techniques for characterization of the elemental composition of planets and planetary bodies. After Michigan, and before coming to the lab, she worked at NASA's Goddard Space Flight Center in Maryland. So now, welcome, Suzanne Nowicki.
Thank you very much, Linda, and thank you for having me tonight. I'm very excited about this talk. The title is Exploration of the Solar System using Gamma and Neutron Spectrometers, but I want to point out that by solar system I really mean planetary science, and this is what I am going to focus on this evening. Okay, so first of all, we are going to start with a little history, and I'm going to explain how the lab started and to develop neutron and gamma ray spectrometers for space applications. So during the 1960s, there was a treaty that was signed between the USA and the Soviet Union that banned the detonation of nuclear explosives in the atmosphere and in space. And so after that treaty was signed, the project Vela was developed at the lab to put satellites in space and instruments that would monitor for nuclear explosion in space and in the atmosphere. And so that's how it all started. Vela was launched in orbit. And it's interesting to note that thanks to Vela, the first gamma ray bursts were actually discovered at the lab. So today I'm not going to talk about gamma ray bursts because this is a branch of astrophysics. So this is not the topic for tonight, but I thought that I would point that out. And I hope everybody can see my pointer, I believe so. Mm-hmm. So here on this picture, you can see one of the Vela satellites on orbit. Here you can see President Kennedy at Sandia National Lab looking at Vela satellites. And here you can see two scientists that are looking at some either gamma ray or neutron detectors. Okay, so next. So on that slide, I want to give a brief overview of the technique and explain how neutrons and gamma rays are used to determine the elemental composition of the soil of planets. So imagine that this is a planet. It doesn't have an atmosphere, which is why the sky is all black. It's got some cool features like some little mountains and imagine, for example, it's the moon, because, it's gray. It doesn't really matter. So in space, there are radiations that travel, and some of them are called galactic cosmic rays. And galactic cosmic rays are interesting because they have very high energies. And most of them are protons. So those protons can travel through space, and so some of them can actually interact into the subsurface of a planet. And so when those galactic cosmic rays interact, they can undergo different type of interactions. And so here on these little animations, you can see some of them that are interesting to me. So you can see that neutrons and gamma rays are produced as secondary particles. And so neutrons are interesting because the mass of the neutron is comparable to that of the proton. So if in the subsurface of a planet you have a lot of hydrogen, what's going to happen is that your neutron can undergo a lot of collisions, and so that slows down that neutron. And so that's what we call the process of thermalizing the neutron. And so by detecting neutrons and by looking at the slowdown process, meaning the energy of the neutron, you can tell how much hydrogen there is in the soil of a planet. Here you can see that gamma rays are produced. They're usually produced because neutrons undergo inelastic scattering or capture. And so the particularity of gamma rays is that they are characteristic of when the atom is excited. And so the energy of the gamma ray is characteristic of the elements that you find in the soil, and the number of gamma rays is characteristic of the amount that there is in the soil. So having a way to look at gamma rays and detect the energy of the gamma ray, you can determine the elemental composition of the soil. There are also gamma rays that are produced from natural radioactivity, potassium, uranium, and thorium. This is also something that you see on Earth. This is independent of the interaction of galactic cosmic rays. So what we want to do is that we want to use gamma and neutron detectors to look at those gamma rays and those neutrons and determine the elemental composition of planet and bodies. So here you can see that I point out that the depth is about 50 centimeters. Contrary to optical instruments that look at, visible or invisible photons, those type of instruments, optical instruments, they make very pretty pictures, but they don't go under the surface of the soil. It's only the micrometers, which is why I pointed out that this technique is very unique because you do not need to drill to actually probe the subsurface of the soil. And I put 50 centimeters, of course, that's going to depend on the composition of the planet. It can be down to 1 meter really with neutrons, but with gamma rays, it's more on the order of 30 to 50 centimeters. Okay. First, I wanted to share with you the type of data that we get from a gamma ray spectrometer. So here I picked the Mars Odyssey gamma ray spectrometer. And so here on the left, you have what we call a gamma ray spectrum. So this is the number of counts as a function of the energy. So the number of counts is the number of gamma rays that interacted in the detector, that the detector has seen. And then the X here is the energy. And so what you can see is that we have lines, and you can see that those lines are labeled. So they are labeled by isotope. And so here I zoomed on this one in particular, here. And you can see that those peaks are labeled. You can see silicon, you can see hydrogen, you can see thorium, you can see sodium, and you can see silicon again. And so this line here, I picked to zoom on this one because this one has hydrogen. And so hydrogen is a very important element for the human exploration program and to characterize water, because in the molecule of water, H2O, we have H. So H is, very important to detect. And you can see that the energy of this gamma ray line is about 2.2 MeV, or mega electron volt. Okay. So on that slide, I'm going to talk about some of the neutron and gamma ray spectrometers that were sent to these bodies or planets. And this is not to scale, okay, first of all. And the gamma and neutron spectrometers that I'm presented are all from USA-led missions. There are some other countries that have, put neutron and gamma ray spectrometers to go to the moon or other bodies. But I'm not going to talk about them tonight. I'm just going to focus on the USA, but, Japan, Russia, China have all sent either neutron or gamma ray spectrometers as well. Okay, so first of all, I'm going to talk about the Messenger mission. So the Messenger was a spacecraft that carried on board a gamma ray spectrometer and a neutron spectrometer that you can see here. It flew by Venus before reaching Mercury, and then it made measurements on orbit around Mercury. So you can see the gamma ray spectrometer here and the neutron spectrometer here. And here, this is the date of the mission. So 2004 was when it launched. 2015 is when the mission ended. Here, all these instruments, they went to the moon. The Rangers missions in the 1960s were led by the United States, and the goal of those spacecraft was to reach the moon and take some data, but they did not achieve their goal. However, the gamma ray spectrometers that were put on board the Rangers mission went into deep space and did acquire some data. And then after the Rangers mission, we had the Apollo missions. Here, you can see the gamma ray spectrometer that was put on the Apollo missions. It did go to the moon, and it did take measurements about 20% of the moon. Unfortunately, most of these data were lost because back then, same thing for Rangers, NASA did not have a good archive system. So after that happened, they actually realized they needed to do a better job, and so they put in place archive system that now everybody uses. That's called the PDS system, Planetary Data Science, something like that. Anyways, it doesn't really matter. So after the Apollo missions, we had a Lunar Prospector. So Lunar Prospector carried a neutron spectrometer as well as a gamma ray spectrometer on board. This mission was very successful. After that, it was followed by LRO, the Lunar Reconnaissance Orbiter. And this is a neutron spectrometer instrument that is still operating around the moon. Let's move to Mars. So the Mars Odyssey mission carries on board a neutron spectrometer and a gamma ray spectrometer, and it's still operating today, so it's been a while. The gamma ray spectrometer, unfortunately, had to be turned off, but the neutron spectrometer is still running and is still acquiring data. So that's really, really great. This instrument was put on MSL, the Mars Science Lab, which is on the Curiosity rover. And the particularity of this instrument is that among all the instruments that I'm showing, this is the only one that is not an orbiter. It has landed. It's on the planet. It's roving, and it has a neutron spectrometer as well as what we call a PNG, a pulse neutron generator. So the pulse neutron generator activates the subsurface of the soil, and it provides more statistics. We don't have to rely on the galactic cosmic rays to produce the neutrons and the gamma in the subsurface of the soil. And so this instrument is called the dynamic albedo of neutrons. Here you can see the near Shoemaker neutron and gamma ray instruments. And so you can see that it's one block, but it actually carries both the neutron and gamma ray spectrometer. So near Shoemaker went to Eros. Here, little Eros that you can see. This is an asteroid. It was a very successful mission. And here, finally, you see Dawn. Dawn also is one block, but carries both neutron and gamma ray spectrometer in one block. And Dawn went to both Ceres and Vesta, which are one of the two most massive bodies of the asteroid belt. So there's a lot of things happening. And so among all these instruments, how many do you think were built by Los Alamos National Lab? I'm gonna let our participants think about it for a few seconds. 4 of them. So Los Alamos National Laboratory built the neutron spectrometer on Messenger, the neutron spectrometer on Lunar Prospector, the neutron spectrometer on Mars Odyssey, and the Dawn instrument. The neutron and gamma instrument on Dawn. Okay, so this is a complex slide. So our participants, if they are familiar with neutron and gamma spectrometers, they're probably interested in the different geometries and the size and the material that were used for these instruments. I'm not going to go into the details because there are too many details, but what I did is that I highlighted in red the type of material that was used for each one of these instruments. And what I want to point out here is that although, they all look different when you look at them. They really look different. But when you actually look at what I point out in red, you can see that most of them, they have the same material. So for example, here you see HPGE, here you see HPGE. A bunch of them, they have plastic, borated plastic. Here you see plastic. B-loaded plastic is the same. Borated plastic, plastic again. You can see sodium iodide. And so although they look very different, they are different, but they use, there are a lot of materials that are commonly used for that type of neutron and gamma ray spectrometers. And even today, we still use those materials to design our neutron and gamma ray spectrometers. But the electronic is really, and the way we read out those materials is really what is improving and where we make progress and what allows us to look at some features that we were not necessarily able to look at earlier on and makes things more interesting. Oh, and I also want to point out that it takes a long time to design instruments for space application, in particular for planetary science. It can take anywhere between 10 to 30 years. And so I personally work on the next generation neutron and gamma ray spectrometers in the hope that I will be able to send it to, a fun body or, be part of a fun mission, something that I will contribute to. And the reason that it's so complicated is because space is a really harsh environment. So when we design our instruments, there are a lot of steps that we have to undergo, and so it can take a long time. The other reason is that if we want to go to a place that's really far in the solar system, like Saturn, for example, it can take 7 years to reach your destination. So if it takes you 20 years to design and build your instruments, it's an extra 7 years to reach your destination. So space is a complicated business. It really is, but it's fascinating. Okay, so since I cannot go into the details of all the instruments that were built at LANO, I decided to pick one of them, and I am going to talk a little bit about the contribution that was made by the Mars Odyssey neutron spectrometer. And so I wanted to show this picture because I like it. It's called the Mars opposition. And so you can see two pictures of Mars, one from 2016 and one from 2018. And you can see that this is the same face that we're looking at, and you can see this common feature here and this common feature here. But you can see the two pictures look different. So you can see that in 2018, it's all orange. We lost, most of the black features that were around this crater. And that's because there is a sandstorm, a huge sandstorm on Mars. So I just thought that I would share that with you because I thought it was interesting. You can also see clouds on the northern hemisphere and on the south hemisphere. And so Mars is tilted like the Earth. And so it has season. And so on the North Hemisphere, the autumn has started in that picture. So I thought it was cool and that I would share that with you. Okay, so this instrument is the Mars Odyssey neutron spectrometer, which was designed and built at Los Alamos National Lab. And this pen here is to provide an idea of the size of the neutron spectrometer. And so you can see that it's fairly small. And now NASA wants to have us design things that are always smaller and smaller, less mass, less power, to reduce the risk and also the cost of the instruments. So without going into too many details, this instrument has boron-loaded plastic detectors. 4 of them. They have this prism shape, and they are read out by what we call a photomultiplier tube. These are the type of interactions that can occur in the detectors and that produce light that is read out by the PMT. And there are also cadmium that we use to shield some of those boron-loaded plastic to eliminate the thermal neutrons so that we can have detectors that are looking specifically at epithermal neutrons and others that look specifically at epithermal and thermal neutrons. And so this instrument is still acquiring data. today, which is amazing because it's been, doing that for a while. And so I want to share with you the type of results that are obtained when we analyze the data that come out of such a detector. And so this is a map of Mars, and by looking at the thermal and epithermal neutrons from that detector, scientists were able to make a map that estimated the lower limit of the water content of the upper meter of the Martian soil. So, like I said, this is not just the surface that we're looking at, this is the subsurface. And so you can see that on the North Pole, we have more than 60% of water ice. And here on the South Pole also, you can see that, there's more than 30% of water that's estimated. And on the equator and the mid-latitudes, you can see that it's pretty dry. And so this, is a huge contribution from the lab to the community, because today these data are still used by NASA to decide, for example, of future landing sites for their mission. So that's very important. Okay. So here, again, I'm going to give our participant a few seconds. What do you think that body is? So I bet most of you said that it was an asteroid. It does look like an asteroid, but this is not an asteroid. This is Phobos, here. The moon of Mars.
Someone guessed Vesta and someone guessed Phobos.
Well, good. That's very good. It does look like an asteroid, though. And you can see also here Deimos, and it also has a weird shape. And so Phobos and Deimos are really interesting because of their shape. One of the hypotheses is that they are asteroids that were captured by Mars, but actually the orbit on which they are is so circular and nice that scientists have doubts, and they are not sure that Phobos and Deimos are captured asteroids because of that circular orbit. Also, Mars, between Mars and Jupiter, we have the asteroid belt, so Mars is on edge with that asteroid belt. So it's not impossible that it would have captured two asteroids. The other hypothesis is that there was a giant impact on Mars, and that created clouds of debris that started to circulate around Mars, and then they accumulated to form both Phobos and Deimos. So why do I talk about that? Well, I talk about that because the Japanese Space Agency is building a mission called MMX that is going to go to Phobos to try to answer those questions. What is the origin of the Martian moons? And it will carry on its board a gamma-ray spectrometer. So I was part of a team at the lab that proposed an instrument for MMX, but unfortunately we were not selected. They selected to put on board a high-purity germanium detector, which has the highest energy resolution. And so MMX is a really interesting mission, in my opinion, because not only it's going to go to Phobos and look for the composition of Phobos to try to answer those questions, but it will also be used to do some technology demonstration validation. And so here, on that picture, you can see people working on a little rover. And so people from DLR, so this is an institution that's German and French. And they are building this little rover that MMX is going to carry and land on Phobos. And so you can see here those little wheels that these people are working on. And those little wheels are going to unfold. There are also solar arrays here that are going to unfold once it lands. And it's called Mascot. And so it's really interesting because on Phobos, you cannot really talk about gravity. It's so small that we talk about microgravity. And so this rover is going to be used to understand how to operate wheels in microgravity. So you can imagine, the gravity must be like very, very weak. So what's going to happen if we have obstacles? Like, is it going to, I don't know. It's going to be interesting. And also MMX is going to return some samples. So it's going to acquire a sample on Phobos and bring it back to the Earth. Okay, that one is pretty easy. This is Saturn. This is Saturn, and here this is the biggest moon of Saturn. This is actually Titan. So Titan is a very interesting body because of what we think it is composed of. So this is a cutaway of Titan. This is an artist view. And so we think that Titan has a silicon core, and then on top of it, it's got like a big ice shell. And then on top of it, there is what we think is a global subsurface ocean. So that's pretty big. Then another ice shell, and finally, an organic-rich atmosphere and surface. And so Titan is really interesting because it's got this organic-rich atmosphere and this ocean. And so we think that these could be the key elements to life. So that's why Titan is so fascinating and interesting. So this is the spacecraft called Cassini. So Cassini was sent to Saturn to study the complex planet and its moons. So the goal of Cassini was to orbit Saturn and orbit the moons of Saturn and look at the rings. And what's interesting about Cassini is that it was carrying with it this probe that we see here. So here they are building, you see it's an ESA probe called Huygens. And we see that people are working on Huygens. And as part of the Cassini mission, Huygens was parachuted into Titan, and it carried, this little probe carried an optical instrument to take pictures. And so it parachuted onto Titan very successfully. And we didn't know what to expect because the atmosphere of Titan is very, very dense. So it's hard to tell what's on the surface of Titan. And so it was really interesting because as Huygens was descending onto Titan, you can see here we are at the top of the atmosphere and we can barely see anything on the surface. And then as we go down, you progressively see more and more features. And when those pictures were seen by scientists, they got all excited because those features could look similar to the ones that we have on Earth. And so they also saw some pebbles that look like they were polished. That makes scientists think that potentially there was some sort of like ocean or river that did that. And so Titan became really, really interesting because of that. So there is a USA-led mission called Dragonfly that has the goal of landing onto Titan in the future. It should launch in 2027 if they're not late. And so here you can see an artist's view of how Dragonfly would land. So it would be parachuted, and here you can see it's a octocopter, and it's going to land. It's going to have its little wings and its little feet, and it's going to land on the surface of Titan, and it's going to deploy its antenna because there is no communication relay. That's why it's got this antenna that is being optimized for communication. And it's interesting to note that it takes more than 2 hours to get the data back and forth. For comparison, it takes about 15 minutes on Mars. So 2 hours is a long time. And so because the atmosphere of Titan is so dense, it's 4.4 times denser than the Earth, this octocopter, can fly easily. And I've heard that if humans had wings and could go onto Titan, we could fly. So that's interesting. And so it's an interesting way. It's very different than a rover because it can fly to, it can land and then it can acquire measurements and then it flies and then it go to its its next destination, and it acquires measurements and then flies again. So it can travel pretty far. It's very different than a rover. So I hope it's going to be successful, but it's very exciting. And so here I want to, Dragonfly is going to carry a suite of instruments. And I'm not going to talk about all the instruments that are being built for Dragonfly, but I'm going to talk about a few of them. Like you mentioned, before I joined Los Alamos National Lab, I worked at NASA Goddard Space Flight Center, and the instrument that I worked on at NASA Goddard Space Flight Center was picked to be put on Dragonfly. And so here you can see the test site where I worked at NASA Goddard Space Flight Center. And you can see a PNG, a pulse neutron generator, a high-purity germanium detector, and 2 neutron detectors. And so although it's going to be packaged different, these instruments are going to be put on the Dragonfly, the octocopter. And so this would be the neutron generator to activate the subsurface of the soil, and this would be a gamma detector that detects gamma rays. So it's interesting because Titan has such a thick atmosphere that galactic cosmic rays cannot penetrate and reach the surface of Titan. So you have to carry on board a neutron activation source. So this is why we're using a PNG for Titan. And so the other thing that I want to point out, so you see that shape here, at the back of the octocopter. This is what is going to carry the power source for the octocopter and for the instruments. And this is an RTG, a radioisotope thermoelectric generator. And so I wanted to point that out because Los Alamos National Lab makes the plutonium pellets that then go into the RTG. So this one is a picture of the one that is being carried by the Perseverance rover that's going to land very soon. So this is going to be a very interesting mission, and I'm very excited to see the type of results that we're going to get out of the instruments. And that's the end of my talk. Thank you very much.
Fantastic. Thank you so much, Suzanne. It's just, it's marvelous. It's marvelous to know what we can learn so far away from home.
I hope I was able to capture people's imagination because this was, the goal of my talk. I mean, instruments are very interesting, but the objective of these instruments is, to understand better how our solar system formed, and it's really fascinating.
Right. Yeah. So one of the questions that came in, I think you'll agree with. They say, if the giant, so when you were talking about the impact theory versus the asteroid capture theory, and if the giant impact theory is correct, Emma writes, would it mean that the moons would have the same composition as Mars?
Yeah, yes, that's something that I should have mentioned. That's the idea. We're going to, measure the composition of Phobos, and then if it's different, then most likely it's an asteroid. If it's the same as Mars, then it's most likely it's the giant impact. And by the way, the giant impact is also the leading hypothesis for our own moon, the Earth's moon. We think that there was a giant impact, and that formed our moon.
Yeah,
Mm-hmm.
yeah. And so maybe that's a method that's been used, that it's just one of the standard methods for forming moons.
Yeah, that could be, yeah.
Yeah,
Mm-hmm.
yeah. So here, Donovan asks a question. Given the variety of gamma detection used in various missions, how important is energy resolution to the possible measurements? So he must mean the energy of the gamma ray?
I think what he means is how important it is to be able to distinguish. I wish I had a better slide. So here you can see, I think what the question is how important it is to differentiate this peak from this peak from this peak. Because if you have a bad energy resolution, then all three peaks would appear into one peak? So that's a very good question. It actually depends on the mission and the type of requirements of the mission. So for example, if we talk about Psyche, Psyche is a metal asteroid. That's another USA-led mission that we're gonna go to, and for Psyche, another high-purity germanium instrument was selected for the mission because since it's a metal asteroid, it was important to get the best energy resolution to be able to separate the metal lines. So I guess this is, this question is, it depends on the mission. It depends what elements we are trying to look at, and that is going to drive the energy resolution and the type of material we want to select for the mission.
So I have to ask this question from Maury because he's asked it twice. Why use CZT? And you're going to have to explain what CZT is.
Okay. Why use CZT? Okay. So high purity germanium is great. I love high purity germanium because you can see the results right here. I have a slide in my backup slides that maybe I should show that. So keep that in mind. You see all the beautiful lines. I'm going to show you some some other materials, and I guess that's going to make the point. I'm getting there.
Aha.
So you can see this is also a high purity germanium. So you can see all the beautiful lines. This is awesome. But then when you get to here, near Shoemaker. So near Shoemaker, the outer detector is a BGO and the inner detector was a sodium iodide. And so you can already see the improvement of the inner detector versus the outer detector. And so what was the question again? Oh, CZT.
Why use CZT?
Yeah. So CZT can provide energy resolution that is close to that of high purity germanium. The issue with high purity germanium is that you need to cool your instruments to a temperature of 77 K, so cryogenic temperatures. And this is complicated to do. And so it requires more mass because you need to add something to cool your detector, although it can be a passive radiator. But so you need to add something to cool the detector, and so it's more mass, more costs, more risks as well, because if it fails, then you have nothing to cool your detector. So the advantage of a CZT detector is that you can get an energy resolution that approaches that of HPGE, but you don't need to cool it. It works at ambient temperatures. So that's a huge advantage.
Yes, indeed, indeed. This is an interesting one from Sean. Are there any efforts by our laboratory to work with SpaceX towards supplying instrumentation such as neutron detectors for future Starship flights?
I don't believe that SpaceX builds neutron spectrometers.
No, I guess he's saying that we would build it, but are they interested in putting anything from us on their flights?
So SpaceX to me is a way to get to somewhere. So they don't build spacecraft, is my understanding. There are your ride to the moon, or your ride to the orbit. So you can just go to them and say, hey, I want a ride, and they will tell you, okay. They are going to give you a cost. They are going to tell you, they are going to ask you where do you want to go, and then they're going to offer you a ride, and then you're just going to, put your instruments to go wherever you want.
Basically drop you off just like a bus route.
Yeah. Yes.
Right.
Yes.
Let's see, a couple very interesting ones here. What's the benefit of having a spectrometer on the surface of Mars as opposed to in orbit?
So I think that one of the reasons they wanted to put the DAN instrument on Mars one thing that NASA really likes to do is to cross-check everything. So if you put an instrument on the surface, you make very accurate measurements at a very small location, and then you can compare that to the data that you get from orbit, and hopefully they are going to match. And if they don't match, then there's a problem.
Sort of an independent verification.
It's an independent verification. Plus, I think that one of the goals of Curiosity was to assess the amount of hydrogen that there was on the path of the rover.
Yeah.
So they wanted neutron spectrometer there.
So related question, how close does the detector need to be to a planet to get useful measurements? Is there any potential of using such detectors from a distance without being on the surface? So sure, right? But how close does it need to be to get useful measurements?
Yeah, so you can see, you can see that, from Mars orbit, which I think gets as close as 300 kilometers from the surface. You can get data, but it takes a long time. So usually we accumulate the amount of data, from months to years. We accumulate those data and then we analyze them, because yes, galactic cosmic rays have to interact with the surface of the soil to produce the neutron and the gamma rays and come back to the detector. So it takes a long time. So that's also the advantage of landing an instrument with an active source. You get measurements faster. So the typical measurement time of the dynamic albedo of neutron is 20 minutes. And then it continues, it goes to the next spot, and then another 20-minute measurement. And also it has the ability to work in what we call passive mode. So if you turn off the pulse neutron generator, you can still acquire data with your neutron spectrometer, and the neutron and gammas that are produced are from the galactic cosmic rays as opposed from the PNG.
Yeah. It's weighing the differences of what it costs and the time that you have to make your observations. Putting something on the planet, on the rover, gives you much more immediate with a source.
Right.
Yeah.
So the advantage of doing an orbital mission, as you can see here, you can map the entire planet, right? If you look at the data from the DAN instrument, so I've got that in some of them on my backup slides. It's just a traverse, basically. It's just a traverse, they get data along the traverse of the rover.
Yeah.
But you can't get like the global map of the planet. So
Yeah. A couple interesting questions here. What kind of processing, or is there any processing done on the instrument before the data is sent to us? Or is all the processing done on receipt of the data?
You mean during the on the way to Mars, for example? They turn on and off the instruments to make sure that everything works correctly. For example, if we go back to Messenger, they launched Messenger, and then when they passed by Venus, it was a flyby around Venus. They turned on the instruments, they acquired data around Venus, and they used it to actually calibrate their instruments. And then they turned it off, went to Mercury, turned it back on.
But those data are sent back to us. We analyze it here?
Yeah.
Yes. That's I
okay.
think, the key there,
Okay.
that it's not being analyzed on the instrument itself.
There's some processing that's done, on board, because the amount of data that we can transmit is limited. But the analysis to make those maps, etc., everything is done.
Yeah.
After. Yeah.
Yeah. What are the methods used to retrieve the data from the detectors?
The methods that are used to retrieve the data.
But maybe that's the question. Do we retrieve the data, or are the data sent to us and we intercept them?
Yeah.
Yeah.
They are transmitted, right?
Yeah.
Either through relay. So on Mars, Odyssey acts as a relay to transmit the data, or on Titan for Dragonfly, it's going to have its own antenna here because there's no relay. Cassini crashed on Saturn. Cassini is gone. So we cannot use Cassini to relay the data. Yes. Yeah.
Is Cassini's dead now?
Basically, yeah.
Yeah. Let's see. Emma has another kind of technical question. She's thinking hard here. What is the angular field of view for orbiting gamma ray spectrometers? In other words, can you see gamma rays coming out at angles not directly going to the detectors?
Not going directly. Well, if you miss the gamma, you can't see it, right?
Yeah.
It's gone. But the field of view, it's interesting because, so we were talking earlier, landed versus orbital. And so one thing is, for example, for Mars Odyssey, of course, your field of view, it will depend on how far you are from the planet, right? The closer you are, the better the field of view. I mean, the smaller. The scale, right? And so one criticism of neutron gamma, especially, Mars Odyssey, for example, is that the spatial scale is about 300 kilometers. So that's pretty big because if you think about the human exploration program, they don't want to, if the data says, well, within this 300 kilometer, we know there is water, but your astronauts, they land 200 kilometers from the water, this is an issue. So NASA would like to have a way for us to fix that and get better spatial resolution.
Yeah.
So this is an interesting question. And we also want to do that because we want to correlate this data with the geological features that are seen with other instruments.
So following up in a way, speaking of data transmission, what facilities usually receive the data? Do we have antennas at Los Alamos National Laboratory, or does NASA usually handle such things?
That's not my area of expertise, so I'm not sure I can answer that question. Maybe there are people in the audience who would be better qualified than me to answer that question.
So if you were to analyze data, because you've made mention that you help design instruments, but you also analyze data.
They're on the PDS. So you go to the NASA website and then you download the raw data and then you work with them. So it's kind of like a black box to me. I don't necessarily have to think about it. Just go to the PDS.
So it's in this universal data archive now that you're able to go to.
Yeah.
And how it gets there, you're not quite sure.
Right. I'm not sure.
Interesting. Yeah. And is that data archive used by all sorts of countries to put their data into?
It's open source.
It's open source.
So anybody can technically, anybody can go there, download the data, look at them, manipulate them.
How interesting. Could it be something that there could be a citizen science project?
Yeah, there's a lot of that.
Cool.
NASA encourages that a lot. You see sometimes call, on Facebook or on social media where they say, science citizen call and
so
encourage people to use data and,
How would a person who might be interested to get involved in that data analysis find a citizen science project that they might be able to join in on?
I think it's very easily to find on NASA website where if you just Google citizen science, there are lots of things that going to come out, and I think it's very easy. I mean, I've never done it personally, but I've seen it often. I believe it's easy to do.
That's pretty exciting.
Yeah. There's a lot of things happening.
Yeah.
Yeah.
What kind of knowledge or skills might a person need to have in order to participate?
Sometimes it's very easy. Sometimes they encourage even kids to look for the data and find something. They make it easy, but I'm not too familiar with it, so I don't think I can really answer that question.
It could be the range.
I think so. I think it could be the range.
Oh, that's fascinating. That's marvelous. That's marvelous. We have time for a few more particular questions. Donovan asks another one. For active neutron systems, what type of neutron generators are used?
Usually something that can give 14 MeV. So because you want to look for energies of gamma rays that go up to about 10 MeV, because there are some interesting lines, such as the lines of irons, that are pretty high. So to make those lines, to excite elements and produce gamma rays of, let's say, 8 MeV, you need an activation source that is at least 8 MeV. So you want to use something that's usually 14.1 MeV. So that reaction would be called a DT reaction, deuterium on tritium, and that gives out 14 MeV neutrons.
So that would be the source.
Mm-hmm.
Yeah.
Yes.
Yeah. Let's see. Everybody's asking such nice questions. I appreciate it. Thank you, you folks out there. Let's see. I'm sure I missed some. An interesting thing here, because you mentioned some of the materials. Why use plastic for the instrument's construction? Does metal alloy interfere with the data?
No, plastic is used as something we call an anti-coincidence shield. So you want to see gamma rays going into your detector, but charged particles, galactic cosmic rays themselves, can go through, and they will create a signal. And so you need to be able to distinguish your galactic cosmic rays versus your gamma interaction. So if you have a gamma detector and you have, sometimes we call it a sandwich around it, that's plastic here, your galactic cosmic ray is going to go through the 3 layers, the plastic, the gamma detector, and the plastic, and leave a signal in the 3 of them. If you have a gamma ray, it will go through the plastic, and it will interact in the detector and be absorbed. And so it will leave signal in only the plastic and the gamma detector. And so that's how you know that it was a gamma ray, and you can get rid of the galactic cosmic ray. So that's how we do it.
And it's a boron plastic?
So that depends. If you use it as an anti-coincidence shield, you don't need necessarily boron. You use boron if you want to look for thermal neutrons, because there's a reaction called capture reactions that occurs with boron with a high cross-section. So you load your plastic with boron if you want to look for thermal neutrons. It's complicated.
No, but I mean, this is people, I'm sure they think about, the periodic chart is finite, but there are, as you know, until we discover another element, but they all have their tremendous uses, and that's something that I find so fascinating about what Los Alamos National Laboratory does, is that they're looking at everything across the periodic chart and what are the special uses that can do things for us. And we might not have a special use today, but we might tomorrow when we're going to, explore something else. So. Well, this was just fascinating, Suzanne. Thank you so much. We're out of time now, and you did a marvelous job.
Thank you very much.
Thank you so much for being with us.
And I just want to point out that in the background on this thank you slide, this is one of the, that's an artist's view, but this is an artist's view of one of the moons of Jupiter called Europa. And Europa is another fascinating body. In a similar way to Titan, we think it's got a global subsurface ocean, and so there is interest from the scientific community to go to Europa and study Europa, and I would love to put a neutron or gamma spectrometer.
So there you go. That's the opportunity for that next generation of explorers like you. You've got to be young to be an explorer, right?
Yes.
Like you said, it might take 20 years to
Yes.
develop an instrument, and then it takes 7 years to get there.
Exactly.
So great. Well, thank you so much, and good luck with the rest of your wonderful career here at Los Alamos National Laboratory.
Thank you so much for having me. It was a pleasure.
You're very welcome. Thank you. And thank you all so much for joining us today. I hope you'll join us again next month at Science on Tap. Bye-bye.